All right, this is our last section in chapter 3. We're going to be getting into the plate boundaries now. So going back to, plate tectonics. So here are some of the plates we have on our planet. Actually, this might be all of the plates we have on our planet here. And so you look at that, though, like as you take a cross section through the Earth. So here are our continents with our crust. And then we have the ocean. You can see that some plates have some continent and some ocean, like or even our North American plate. Like the North American plate extends well beyond the eastern coastline, way out until you get to like Iceland out here. Then, so we have the ocean and the continental crust. All of this is crust, and that is on the mantle. And the mantle is broken into two sections or two layers based on how it flows. And we have a more elastic material we call the lithosphere right underneath the crust. And then we have the asthenosphere, which is plastic. And again, that's going back to the deformation we just talked about. So rocks in this layer are more elastic, and then the deeper you go, they're more plastic. Yeah, so because these move so easily, this is why I said it's not really like the continents floating on water like a log would. It's more like they're like moving on a conveyor belt of slime, more or less. The deeper you go, the warmer things get, so they kind of start to get a little melty, a little like a hot chocolate chip cookie kind of will. Plate boundaries. All right, so we have three major types of plate boundaries. We have divergent, convergent, and transform. This one is on divergent. And so this is where the two sides move apart from each other. It can start anywhere. It can start in the ocean. It can start in the continent. And if it continues long enough, it always ends up turning into an ocean. So if you think all of a sudden currents in the mantle start pulling apart underneath, this is pulling left, this is pulling right, it starts dropping this down. Again, if you think of like your slime, and you take your slime and you start pulling it apart, that bottom is going to the bottom, but in between your hands is going to get thin. And as it thins, it's going to lose some structural support, and it's going to start dropping down. And so that happens. It drops down low enough. You can see it's thinned here, thinned, and drop down. Water is going to fill up where it's dropped down, and eventually it'll turn into an ocean if it keeps spreading and gets far and far enough away from each other. As it spreads, because it's so thin, there's not much pressure pushing down on the mantle, so the mantle can kind of come up, and that's where we get a lot of these volcanics in the mid-ocean ridges, and then the volcanoes ultimately is what causes all of the mountain ranges right there. And then it gives some examples. We've got the Mid-Atlantic Ridge, the East African Rift, and the Rio Grande Rift. So this is in the ocean, and the rifts are still on continents. And then we do get a lot of volcanic and earthquake activity because things are moving. All right, convergent. This is the opposite. This is where the two plates are being pushed together. So with this, there's actually kind of two subtypes of subduction zone or of convergent plates. So one is subduction zone, and this is where the oceanic material is colliding with continental crust. The continental crust is very silica rich, where the oceanic material has a lot of iron and magnesium in it. So it's more dense. It likes to sink. So it goes underneath the continental crust. When that happens, you heat up a lot of the ocean water that's coming and being subducted with it. The ocean water heats up, and that melts this material here. And so you start getting these magma chambers, and then you get volcanoes right here. This is also where you find the trench, those deep trenches we talked about, like the Mariana Trench, which is really famous. Those are all subduction zones where it's just being pulled down. And I don't think they still haven't found the depth of that trench, I don't think. If it happens where two oceanic plates are coming together, you get these ocean islands. This is like the Aleutian Islands by Alaska. And then you can have it here where two continental crusts are colliding. In that case, it's really like nothing wants to go down. So all of this continental crust won't really subduct. This is the lithosphere here that's subducting. The continental crust stays and kind of pushes up, and then you get these huge mountain ranges. And this is like the Appalachians, or not the Appalachians, I think it was, but they're not huge. The Himalayas. The Himalayas are currently doing this, so that's why they're so big. The Appalachians at one point used to be that big, but they are so old now they've weathered away. Okay, I think I covered everything there. Transform. So this is not pushing, not pulling. This is side by side. So this is when one plate goes one way in relation to the other plate. This is California here because I think the San Andreas is, at least in America, the most famous transform fault, if not globally. And with that, you get a lot of earthquake activity because, well, anytime things are moving, you're going to get a lot of earthquake activity. And then there's this other thing called hotspots. It's not on a plate boundary. This is within a plate. And there are these more or less random areas of volcanic activity that they have ideas what causes it. One of the ideas is like a bump on the core within the Earth, like in the center of the Earth. But I don't know how much evidence there is to really support that theory. So it may or may not be true. Let's see, we have Hawaii is a hot spot, so is Yellowstone is a hot spot. But anyways, the hot spot stays the same. And as you have the plates moving over the hot spots, you get these chains. And so you can kind of track the direction of where these plates have been, which direction they're going, looking at these the historical evidence of the island chain. And this is just the direction of which the different plates are moving in relation to each other. These are vectors, so the longer the vector, the more speed there is, and then the direction. And so if you look at the transform fault, the San Andreas, it's always interesting to me that really both of these arrows are pointing left. But again, it's in relationship to one another. This is going up just a little ever so slightly. And their speeds are a little different too. Let's see. So what causes them to move? Convection cells in the mantle. This is your lava lamp example. So as you heat up that lava lamp material or that slime or silly putty or whatever, heat rises. And so it comes up and then eventually it cools and it sinks back down. And so we have this going on within the mantle, and everything on the crust is just kind of going for the ride. So where it's coming up, we have new oceanic crust is created. And where it's coming down, it's kind of remelting. Yeah, it's cool. Subduction zones. So there was, at one point in time, I guess, a debate. Was this pushing it along or was this sinking and pulling it along? I think they've now just realized it's a little bit of both happening all at the same time. And that is it for chapter 3.